I would like to say that there is, of course, the figure of André Fliguer is looming very large over this conference. And even though I'm not in this field, so I haven't been very familiar with André mathematically, as a Swiss, I have, of course, met him many, many times and enjoyed his very nice personality. And in fact, I just thinking about this talk today, I realized that the very first mathematical talk I've given in my life was, in fact, at the invitation of André, who invited me to, I was a student at the time. I met him in Zurich, and he invited me to Geneva to give a lecture. And that was the first time I ever gave a math talk. Anyway, so this lecture contains the title, the word bounded cohomology in the title. And I decided that I was going to spend quite a bit of my limited time in trying to justify a little bit why anyone should care about something that has such a strange technical name as bounded cohomology. And so I'll try to spend a good part of my time trying to give you at least some, try to tempt you to join maybe this enterprise to study cohomology in this strange bounded way. And then I only take a little bit of the third chapter of today's lecture to tell you about the other point of my title, which is ergodic methods. And there again, I'll try to take the simplest toy case to try to invite you to consider also perhaps using such ergodic methods. So I'm going to try to give you an example that can be completely described in a lecture without getting technical at all. So first, why bounded cohomology? And of course, what is it? So why? You might have noticed that I write very badly, but I erase very well, so I'm compensating. So I didn't erase these blackboards, that wasn't me. I did the good ones. So why bounded cohomology? And so the notation, there's a cohomological notation, Hn, and we put a little b to say bounded cohomology. Why bounded cohomology? So if you look at it without stepping back enough, it looks like a very strange definition, because cohomology, we all know, is cocycles modulo coboundaries. And so bounded cohomology will be bounded cocycles modulo bounded coboundaries. And whatever this means, if you say it like that, it doesn't seem very inspiring or very motivated or even very conceptual. So I'd like to give you, to begin with, a few hints why it would make sense to even define such a thing. And you have a fraction here, right, with a numerator, a denominator. If you are very lucky, the denominator could be 0, then you don't quotient by anything. And so a first observation is to say, well, historically it just happens that if you study cohomology, you study cocycles, sometimes they happen to be bounded. So here's an example. Perhaps the cocycle that you meet in elementary school is the area of a triangle, right? That's a 2 form, but you compute areas of triangles in grade school. And perhaps a bit later you learn that in hyperbolic geometry something funny happens. The area of a triangle is at most pi. So it's a bounded cocycle, right? That's an example. And pushing further and much more conceptually in this direction, there's the 1958 paper by Jack Milnor, then generalized by Wood, I believe, in 1973. And this is a long story that somehow reached its climax with Gromov in 1982. And this long story abuts to the observation, vastly generalizing this grade school thing with triangles of area at most pi, that many characteristic classes happen to be bounded. So to output a number, so if you pair it, so you get a characteristic number, that just happens to be bounded, like in the Milnor-Wood inequalities, or like in the area of a triangle. So the observation of this story is many characteristic classes happen to be bounded. So sometimes in the obvious way that I described with triangles in hyperbolic plane, and sometimes in highly non-obvious ways, such as when Goncharov finds a clever cocycle to represent a characteristic class attached to GLN. So that's saying that sometimes we observe that the denominator defining cohomology can be represented by bounded objects. But now there's something else. We have a fraction, so you have to worry about the denominator. And what happens if you make the denominator smaller? What happens is that your invariants become more refined. Because if you study, for instance, characteristic classes, but you identify them only if they differ by something bounded, you are saying that you refine your invariance. So the second source of motivation for this is that you get refined invariance. And I guess one example is the following. If we just go back again to something like the Milnor-Wood inequality, so something that concerns circle bundles, it's I guess an exercise that the Euler class of a circle bundle, or seen differently, if you have a representation into the homeomorphism of the circle, that the Euler class of that will vanish if and only if you can lift your action to the line, right? This Euler class is really the obstruction to lifting the action from the circle to the line. And if you ask when this Euler class, which happens to be bounded, can be trivialized in a bounded way, so when this denominator here is also bounded, this is essentially if and only if this action has a fixed point. So if you have a fixed point, of course you can lift to the universal cover, but it's a much stronger statement. So this is a theorem of Etienne-Gys that the Euler class, as a bounded class, tells you essentially if the action has a fixed point rather than just can be lifted. So one way to say that is that it also leads the same type of examples to the notion of quasimorphisms that we've heard about in this conference already a few times. Because what is a quasimorphism after all? So again, you have a very down-to-earth, naive, unenlightening definition, which is it's a map from a group, let's say to R, which happens to be almost a homomorphism, so the sup over x and y in the group of the mistake that you make if you try to check if it's a homomorphism, f of x plus f of y minus f of xy. This supremum should be finite. But conceptually what this means really is that you observe here a bounded cocycle, which is a cocycle for the trivial reason that it's actually a coboundary. But the interesting question is this trivial object actually trivial in the bounded world? Namely, this function f, whose coboundary is bounded, is it itself bounded, or is it at bounded distance of an actual true homomorphism, right? So the question of triviality or not of quasi-homomorphisms is really a question about H2 bounded, right? So here you're playing with the denominator, and if you do something like, I don't know, the Smiley-Toayev theorem that the Euler class of a even-dimensional vector bundle is bounded by something like 2 to the minus the dimension, you're playing with the numerator of this thing. Now, yet another reason to want to consider bounded cohomology rather than cohomology is a question of continuity. So this third motivation, I call it continuity, is more algebraic, and it starts with the observation that the cohomology of a group or of a space, but I want to emphasize the group case here, the cohomology of a group, you can think of it as a particular case of a completely algebraic construction. So the ordinary cohomology of a group G is tautologically the same as the cohomology of the algebra associated to the group. So this is really a tautology, right? If you linearize the group, you say that you allow yourself not just to multiply elements but to take formal sums. Then you can consider cohomology of this algebra. That's a much more general object than group cohomology, but it just boils down to the cohomology of the group. Now what happens is that this algebra, it's somehow the free algebra on the group G. We are allowed, of course, to close our minds to the fact that it also carries a free norm, right? So if you make a formal sum of group elements, you can ask how many elements did I sum and with what coefficients. That's a norm. That's the free norm, the projective norm associated to this construction, or analysts will call this the L1 norm. And you can say, well, after all, let's not close our mind to the fact that we have a topology now, and so we should look at the cohomology of this topological algebra, or this this normed algebra, sorry. And so this has been studied systematically shortly after cohomology was studied systematically for algebras, and that's the memoir of Barry Johnson in 1970. So if you look at the cohomology instead of the normed algebra RG, or you can complete it and then you get the classical convolution algebra that you have in functional analysis, L1G. This will be tautologically the same thing as the bounded cohomology of the group. And why is that? That's simply because if you ask when is a linear functional continuous in this norm, it's if and only if, as a function, it is a bounded function, right? The dual of L1 is L infinity. So that's not a reason to consider bound cohomology. And indeed, you can see there's a particular case of the cohomology of Banach algebras. And in Johnson's memoir, this particular case actually occupies most of his memoir. And then it's 12 years later that Gromov has somehow rediscovered the importance of this cohomology. Yes? Oh, HN, thank you. So I have this thing that I always confuse the number 2 and the letter N. Don't ask me why, but it's a fact. It always happens. So, yeah, in both directions. Yes?
So I know you have given a super precise definition of bounded cohomology.
I haven't.
But in the bounded co-boundaries, are the co-boundaries supposed to be bounded, or are they co-boundaries of bounded objects?
Of something bounded, yes. Excellent question, right? So it's really, otherwise I wouldn't be saying much more than, right? So that's super important, yes. So the co-boundary of something bounded, yes. Yes, thank you. So anyway, this is impressionistic, sequence of name dropping and formula dropping to try to convince you that there's at least something there. And perhaps the last thing I want to stop here with this chapter 1 and right away jump into something more mathematical. So the chapter 2, which is still not the actual content, substance of the talk, I want to tell you that if you decide to study bounded cohomology, then you are probably going to study it from the perspective of ordinary cohomology that you really care about. So you're going to say, as Milnor or Gromov, you're going to say, when is cohomology actually bounded? And if it is, when is the invariance finer, and when can I have a better control on my classical invariance by knowing where it lives modulo bounded things, right? So to make this a little bit more mathematical, we're going to compare the bounded cohomology to the usual one. And indeed, if you decided to settle on some formal definition, for instance, the non-conceptual one here, you see that there's clearly a natural transformation, a forgetful natural transformation, where you say, well, if I have a cocycle or a characteristic class that happens to be bounded, I can forget that it's bounded, and it's still the characteristic class or cocycle. So I have a map like that. And it's well defined because if two things differ by the coboundary of something bounded, in particular they differ by a coboundary, right? So you have a map. It has no reason to be injective because you have this finer equivalence relation here. And of course there's no reason to be onto either because there are many invariants that are not bounded. Okay, so you have a natural transformation that compares the classical invariance to this more exotic invariance. And I want to highlight that there are 3 scenarios. So basically, there's the boring situation where the series run in parallel. So that's the first scenario. And I'm sorry, it's not boring, but it's the parallel results. But it's simply not what I want to highlight in this lecture because that's when things are not unexpected. I just want to state perhaps a model example of a theorem. So I'll start with the theorem of Mather from 1971, which tells us that if you look at the group of all compactly supported homeomorphisms of Euclidean space, right? So you look at the homeomorphism of Euclidean space that are compactly supported, then this group is acyclic, and so in particular, the cohomology of this group vanishes in every positive degree. And perhaps this is a good moment to tell you that in my notation for cohomology, which I haven't defined very formally, right, I'm always implicitly thinking that I have trivial coefficients in the real numbers. Mathé's theorem is stronger. He proves this in the for integral coefficients, but I don't want to go there, right? So for me, implicitly, my coefficients are trivial and real. So Mathé's theorem is that this is an acyclic group, and one of the early and founding results in bounded cohomology is a theorem of Matsumoto and Morita, which proved that exactly the similar statement is true in bounded cohomology. So you see, no surprise. So Matsumoto Morita. It is same for the bounded cohomology. And indeed, even the proof is parallel. So both Mathé's result and Matsumoto Morita's results rely on something that has been formalized, almost turned into an industry later by algebraic topologists under the names of mitotic groups or binate groups or pseudo-mitotic groups or dissipated groups. And the idea is always the same. The idea is that if you look at compactly supported homeomorphisms, and if you look at finitely many at a time, then they're going to be supported in some large compact sets. And the idea, which is at the same time brilliant and a bit tricky to implement, is that if your homeomorphisms, so you look at finitely many at a time, if they're supported on a compact set, you can somehow replicate them. So that's why it's called mitotic. You can replicate them infinitely often, and you can construct, so you can try to copy this here into a smaller version of itself next to it and make infinitely many copies. Okay, so you replicate what you see here infinitely often, and all this still happens inside a big compact set. So that's the fundamental property of this group. It has this enormous elasticity that allows you to see infinitely many copies of itself in itself. The precise mathematical statement is the following: whenever you take finitely many elements in this group, compactly supported homeomorphisms, you can define a new finite family of these homeomorphisms which are still compactly supported, but contain infinitely many disjoint copies, so commuting copies of themselves, right? And when you see that, you see that it's a very powerful tool, and this will then formally just imply acyclicity, right? Then it's a formal matter that whenever you can do that, your group is acyclic. But what you see is that it's very flexible, but at the same time, it's very tricky. Because if you try to do that, for instance, with Diffeomorphisms, forget it, right? You're not, because you have an accumulation point here, right? And it's easy to say that you shrink homeomorphisms and that when they converge, when the supports converge to a point, you decide that this is a fixed point. This is something that's not going to work in the smooth category. It's not going to work in the PL category. It's basically not going to work unless you're in a very flexible category like that. So it would work, for instance, if you study transformations of, I don't know, Cantor space, right? And it works very well for homeomorphism of RD, but okay, not beyond. That's the parallel scenario. Now there are two more scenarios among my trichotomy. They are the surprises. So they're the bad surprises and the good surprises, right? So number one is no surprise, and then there'll be bad surprises and good surprises. So let me start with the bad surprises. And the bad surprises are really bad and account for the fact that progress in bounded cohomology is slow and frustrating. So let me give you some bad surprises. Second scenario, bad surprises. And I'll start with perhaps the most depressing fact, which is that if you want to study the cohomology of a group, perhaps you should start with the very simplest groups you can imagine, and then build more complicated groups by elementary operations or spaces, same. So the simplest space I could imagine for the purpose of cohomology is a circle. the simplest, non-trivial, homologically non-trivial space. And then if I take two circles and I try to glue them along a point, I get a figure 8. And the bad surprise is that already there, nobody knows what the bound cohomology of this space is. So from the group theory viewpoint, I'm talking about taking the free group on two generators, and nobody knows what the bound cohomology of the free group looks like. Okay, so first bad surprise. The bounded cohomology of the free group, or of a non-commutative free group, which we can think of as the bounded cohomology of this space here, okay, nobody knows what it's like. And the little that we know is really shocking. So we know, for instance, that in dimension 2, this is a one-dimensional object. It's a one-dimensional group, right? But in dimension 2, this is already an infinite dimensional space. So it's non-trivial and of infinite dimension. And I'm going to give you a proof that it's non-trivial. Right? Oh, by the way, historically, the fact that it's non-trivial has actually been discovered by Johnson in 1970. So before the term bound cohomology existed, Johnson already wrote down the quasi-homomorphism of the free group, and long before Bob Brooks. But let me give you a much simpler proof. I'll give you a completely elementary proof. So that, I mean, it's a plausibility argument if you know a little bit of group cohomology, it's actually a proof. So if you have a large group and a smaller subgroup, you can restrict the cohomology from the larger to the smallest one. There's a pullback functor, right? And of course, if your smaller group is, let's say, of finite index, this pullback will be injective because you can average over the coset space. So that's called transfer. This also works if, for instance, your group is a co-compact subgroup of a larger group, right? You can also transfer, or at least in the, if it's co-compact lattice, let's say you can average over the quotients, that's still a transfer, so restriction is injective. So take the isometric group of the hyperbolic plane, right? This certainly has orientation preserving. So this is this famous 2 form that we discussed before, the area of a triangle, which is bounded, area at most pi. In there, I can see a free group as a lattice, so discrete subgroup of finite covolume, as Gauss nu, for instance. And so that means that I can try to take this 2 form, area of triangles, and restrict it to the free group, and I should get a 2-dimensional cohomology class, right? Except that's nonsense, because we know the free group does not have 2-dimensional cohomology. So what goes wrong? What goes wrong is that when you try to average it over the quotients, you'll have the problem that this quotient space, and again, as Gauss knew, it has finite volume, but it has a cusp. It's not compact. So if you try to average a function, you might run into a problem. You might not be able to integrate it if it's not bounded. But the area is bounded by pi. So what goes wrong? What goes wrong is the denominator of the definition of cohomology, that the 2 form of the hyperbolic plane as a cohomology class for the free group must be trivial because the free group is one-dimensional, so it is trivialized by something unbounded. In bounded cohomology, it's not trivial for the same reason, right? Because bounded functions, you can always average them over something of finite volume, cusp or no cusp. So that's a proof that the free group, not only it has bounded cohomology in degree 2, but a very explicit thing. It has you can take the 2 form of the hyperbolic plane and restrict it. And you can restrict many other things, and you'll get infinitely many different linearly independent classes. Now, that's a bad surprise, right? And actually, the same happens for surface groups or surfaces. We also don't know. We also know that it's wild in dimension 2, but we have no idea what it is, for instance, in dimension 4. What we do know, and this is something that I can explain in this community here, is that it is non-trivial in dimension 3. If you take a hyperbolic surface, then its 3-dimensional bound cohomology is non-trivial. And that's also a bit shocking, right? And here's why. Because we know that you can construct a hyperbolic 3 manifold. So if I call the fundamental group of that, okay, so you know that you can do the following. You know that you can take the pi1 of the surface and take the mapping torus, so the semi-direct product if you take a suitably chosen diffeomorphism of this surface, the mapping torus will have hyperbolic structure. Okay, and that means that this guy here will have three-dimensional bound cohomology, because just like the triangles have bounded area in the hyperbolic plane, the three simplexes have bounded area in hyperbolic geometry. Actually, every simplex is bounded volume in hyperbolic geometry. And so this gives you a three-dimensional cohomology class, honest cohomology class, the volume form for this mapping torus. And I claim that when you restrict it to the surface group, it remains non-trivial. Very much like when you restricted the 2 form to the free group, it remains non-trivial. So why is that? This time, the surface group does not have finite covolume in this, right? The quotient is Z. But we'll see as soon as we jump into the chapter of tools that Z over Z, you can also average bounded things. That's what Banach did when he invented what we now call Banach limits. You can average over a large interval, so you make a Cesaro average, and this will give you an invariant average, so Banach limit, of any bounded function on Z. So from the viewpoint of bounded functions, Z is just as good as a finite group. And so this is a hand-wavy proof that a surface actually has three-dimensional bound cohomology. And we have no idea what happens in dimensions higher than 3. So these are bad surprises. Let me give you now.
As the proof implies, if you have a high-dimensional hyperbolic manifold, hyperbolic over circle, you're getting non-trivial high-dimensional.
So you'll be able to do that, but I mean, this will not give you something for the surface, right? It will give you something for, so yeah. I mean, so this is a general principle, but yeah. Okay, so the good surprises. It's a pity to use a dirty blackboard for good surprises, but. And I would like then to tell you about ergodic tools to prove these good surprises. If you look back at the first scenario, I mentioned that there's no way to apply Matter's proof to, let's say, diffeomorphisms or PL, and in fact, we don't really know, at least I don't really know, but my understanding is the specialists don't really know what the cohomology is of the compactly supported diffeomorphisms of RD, but that what they do know is that it's a complicated and non-trivial thing, right? So the cohomology of, let's say, compactly supported diffeo of RD, or just all homeomorphisms of RD, or just all diffeomorphisms, so not compactly supported, so all homeomorphisms of RD. And if I take all of them, I better take the orientation preserving ones. Is, I say wild to mean that, okay, it's not completely known, and what is known is highly non-trivial, right? And so now the good surprise is that in bounded cohomology, we know absolutely exactly what happens. And this is the moment to, it's actually almost a bit late, to acknowledge all my collaborators. So I'd like to say that this is joint with Sam Nariman, Francesco Fournier-Facio, and somehow in part also with Alexander Coopers. So you'll notice that I'm violating the alphabetic order because I tried to be chronological. I started working on this with Sam, and then we worked some more with Francesco, and Alexander has provided an appendix for one of our papers. So here's a theorem that we proved. The bounded cohomology vanishes in every degree for all these groups. So the all homeos, all diffeos, orientation preserving, and the compactly supported diffeos, and this in all irregularity and all dimensions. So it's a completely uniform thing, and none of the crazy wild things that happen in cohomology happen here. All right, so I would say there's a nice somehow contrast between spaces or groups that we understand super well classically, but embarrassingly don't understand at all in bounded cohomology, and in fact the little we understand points to wildness. And here it's an ordinary cohomology that we can't yet at least completely understand these groups, these transformation groups, but it's understood that it's going to be rich and complicated. But in bound cohomology, we understand them completely. And now if you go back to the motivational first chapter, you'll see that there's another way to think of that. Namely, it is to say that these complicated invariants that exist or probably exist for transformation groups of Euclidean space, these invariants are not bounded. So for instance, one consequence of our result is that Pontryagin classes in this setting are unbounded, contrary to, for instance, primary characteristic classes such as the Euler class. So you can see it as an unboundedness result, but highly non-constructive. And so now it's time to come to the chapter where I talk about ergodic tools. And the idea is that these are the tools to prove some of these results. And I'm going to choose the simplest possible tool to prove the easiest of these results. And to this end, I'll introduce a few concepts from that can be expressed in ergodic language. So, third and last chapter, ergodic tools. And this leads to at least one proof. Okay. So I believe I'm going to tell you enough to convince you that the group of compactly supported diffeomorphisms, regardless of regularity, can even be PL if you like, is acyclic in the bounded sense. So here are the tools I'd like to advertise. And I'll start with one of my favorite adjectives in mathematical English, amenable. And I'm going to define it not in my favorite way, so that's why I need notes. So recall a group G is called amenable if there exists an invariant expectation on all bounded functions of G. Okay. So what's an expectation? I speak a bit like a statistician. So you look at all bounded functions on your group, and you ask, can I associate to every such function a number, its expected value? And so like an expected value, it should be a positive operation, normalized, right? If your function is a constant, the number will be that constant, and should be invariant under the group, right? So, okay. So that's, then in that case, the group is called amenable, and the examples are, if a group is finite, then you can literally compute the average. But if the group is Z, then that's exactly what Banach did. I mentioned this when I talked about mapping torus. Banach made the observation that averaging a bounded function over larger and larger intervals, if you take an accumulation point of this process, will actually give you an invariant expectation, because as we learn in calculus, when we do infinite sums, infinite series, and we do telescopic sums and realize that Cesaro averages don't really change, right? What we're actually doing there is we're applying Banach's expectation, right? So Z, more generally commutative groups, more generally soluble groups. Okay, so if a group admits an expectation, it's called amenable. Now, a few concepts related to that. But now, finally, in an ergodic language, so I'm going to give you some ergodic definitions. What is the context to be able to give you ergodic theoretical definitions? The context is a dynamical system, so a group acting on a measure space, so a non-singular G space. So let's G acting on some set X be a, in parentheses, non-singular measure space. Measure G space. So I emphasize non-singular just to, tell you in the negative that I'm not assuming that I have an invariant measure. I'm only assuming that that action is not singular, namely that notion of null sets is preserved. But I'm absolutely not assuming that I have an invariant measure. I have a probability space in which I act. Okay, so let's start with a few definitions. First definition, we say that this action is itself amenable if, and I mimic this group theoretical definition, if there exists an invariant expectation, but this time the expectation will be not real valued, but in a sense x valued. So what this really means is that I want to have an expectation from bounded function not just on G, but on G times x, to bounded functions on x. Okay. So the domain here is nothing else than bounded functions on G with values in bounded function on x, right? What computer scientists call currying. So it's functions with values in L infinity of x. So if x is just a point, this is functions on G, and this is real numbers. So this generalizes the Banach's notion of amenability of a group, of von Neumann's notion, by doing it over a measure space. All right. Why do we want this definition? So here's the benefit of this. So here's the usage that I want to make it. Here's the use I want to make of it. The use is then the bounds cohomology of G is computed by, instead of building cocycles on the group G, we can build cocycles on the space X. So I look at cocycles, so bounded functions on X, that are invariant under the group, and if you do the bookkeeping right, if you want an n-dimensional cocycle, it will have n+1 variables. Why is that? Because whatever the explicit computation of bound cohomology will be, it will be something about cocycles on the group. Now the expectation allows you to project them down to cocycles on your measure space. And so that's the heuristics of why, if you want to compute, it's like an ordinary cohomology. If you want to compute cohomology of a group, you very often want to replace the group by some G space. And it could be a classifying space, but it could be a proper G space. And the luxury we have is that since our invariants are bounded, we can average them even over anything that is averageable, which means amenable. Right? So it's basically a tautology that amenability is exactly the condition that allows you to average down your cocycles from the group to some smaller space. Okay, so that's why we introduced this notion of amenable G spaces. And now I want to define the second concept, and it's basically the last one, essentially. I want to define ergodicity itself. That was in the title. This guys can't multitask. There must be a European norm that doesn't allow blackboards to go faster. It's funny, that makes everybody laugh because it's actually true. So I investigate this once, and there's a norm that applies to doors of trains and metros, and I use the same norm for the blackboards so that we don't get decapitated. And, right, so we have a group, for instance, a group of diffeomorphisms of the Euclidean space. We'd like to compute this bounded cohomology, and we know that we could try to use measure spaces if they satisfy these Fournier amenability conditions, and we'll see examples soon. But this by itself is not helpful unless I give you a good reason to believe that such a measure space X can be much simpler than the group, much smaller perhaps. And that's exactly what I want to do next. And the relevant definition for that is ergodicity. So, next definition. A measure G space, so G acting on X, is called ergodic. I believe Boltzmann has coined this term. I have PhD students here, I tell them usually it means hard work, from the Greek word for working. So an action is ergodic if Well, the informal definition is that it mixes the points of X so much that you can't distinguish any invariant, right? To make this formal, you could say that no measurable map on X can be invariant without being constant. And I'm going to phrase it in a simple formula. I'm just going to say that the G invariants among an infinite of X are reduced to the constants. So this is perhaps not a classical definition because, you know, classically nobody would care to consider only bounded functions, but I'm sure you agree with me that if you have some non-trivial invariant, right, then you can make it bounded. Take the arctangent, for instance, I don't know, right? So yeah, it's so ergodicity just means that you don't have, you know, any non-trivial invariants, and so in equivalently any non-trivial bound invariant on your space. That's ergodicity. So what's the benefit and what's the usage of that? Well, let me tell you what the benefit would be of a stronger condition. I'm going to say that this action is doubly ergodic if the action on pairs of points is ergodic. I'm going to say that it's triply ergodic if the action on triples is ergodic. I'm going to say that it is k ergodic if the action on k tuple is ergodic. So I'm going to say k ergodic, so multiply ergodic if, well, the diagonal action of G on X to the k is ergodic, right? And could even dream and say, well, maybe we could call it infinitely ergodic if this happens for all k, right? So now that's a stronger condition. And so what is the use of that? Well, if you combine it with the previous one, you see that the use of that is then, if it is amenable, so before they were on strike, and now it's a French blackboard, I imagine. Okay, the strike again. Okay, the use of that is when this happens, right? When this happens, then the bounded cohomology of G will have to vanish, at least, you know, in degrees less than k. Why? Because we agreed that you can compute the bounded cohomology by looking at cocycles on tuples of points on your measure space, provided it's amenable. So amenability is a way of saying that the space is large enough to capture the whole group. Now, ergodicity is in the opposite direction. It's telling you that the space is actually, in some sense, very small with respect to the group action. So if you can compute the cohomology of the group on tuples of points on X, but if there's no non-trivial invariance on tuples of points, then you have no non-trivial cohomology. And if you keep track of the indices, you realize that, yeah, actually, to get vanishing in degree n, you need to be ergodic in n+1 variables. But, right, okay? So that's the usage of ergodicity. So we have these two concepts, amenability and ergodicity. And now if you want to try to prove that some groups don't have bounded cohomology, all you have left to do is give me a favorite group, say, diffeomorphisms or homeomorphisms or something. You need to come up with a clever way to construct a measure space on which this guy acts. And if possible, the action should be tame enough, regular enough to be amenable, but small enough, wild enough to be highly ergodic. Ergodic maybe k-fold. That's the goal. So here are a few facts. So if you only want to have k equals 1, yes, Mehdi?
Can you say one more time, what was the use of ergodic? You said the use of amenable.
Okay, so the use of amenable was up there, right? And here the use of ergodicity is that if in addition it's amenable,
so it's both
yeah. So the use of ergodicity under the assumption of amenability is that it vanishes. Why? Because amenability told you that you can compute it on X, and ergodicity tells you there's nothing to see on X, right? So is that okay? Yeah. All right. So if you ask me, for instance, let's start small, to just find for group G one space on which the action is amenable and ergodic, that's very easy. You just take G itself, right? The action on G itself is transitive, so it's certainly ergodic, and it's amenable because if you look at the definition here, it's really a tautology, right? So that's too easy. I'm not going to write it. But the first non-trivial fact, which I love, is that for any group whatsoever, and perhaps to be rigorous, I'm going to say that it's countable, because otherwise ergodic theory is a bit hairy. So for any group whatsoever, there exists a two-ergodic, so doubly ergodic, amenable G space. So this, to me, is non-trivial. And in fact, with my PhD advisor, we proved this in a completely ridiculous way by, using the mountain phenomenon for SL2R and an analogous thing for Diffeomorphism groups. And then somebody opened our eyes to the fact that this was known for a long time. And so I'd like to attribute it all the way back to Hopf, but it's not the topologist Hopf, it's Eberhard Hopf, 1937. Garnett, I believe Lucy Garnett in 1983. And I'm going to say etc. because Hopf essentially proved this in a completely different language for the particular case of Fuchsin groups. But if you can do that for Fuchsin group, I mean, you can do it for free group. And in fact, using a bit of ergodic theory, if you can do it for the free group, you can do it for a quotient of the free group. And so then you have all groups, right? But let me tell you what the reason is. The reason is as follows. So I can give you a very explicit construction, and that has been explained to me by Vadim Kajmanovic when I was finishing my PhD. And it's as follows. You choose a random walk on your countable group, right? And you take the Poisson boundary of this random walk. So the space of tail events of the random walk. And I don't intend this as a justification. I just intend this as, telling you where to look if you want to construct that and trying to convince you that it's not a trivial fact. It's a beautiful fact, and somehow it's a counterexample to Gromov's statement that there's no non-trivial fact that holds for all groups, right? So, yeah. So unfortunately, this doesn't go very far because it only tells us that no group will have bounded cohomology in degree 1, since you have to increase by 1. And this we knew, because what is a bounded 1 cocycle? It is a bounded homomorphism. And of course, bound homomorphisms are not trivial. So it's unfortunate. It's a completely non-trivial proof of a totally trivial fact. Right? Next fact. Next fact. For many groups, you can't do any better than that. So for, let's say, the free group or the surface group, the fundamental group of hyperbolic surface, there is no triply ergodic. There's no triply ergodic amenable space. And you know the proof of this fact because I gave it, but conveniently I erased it, so you have to remember it. I gave you proofs that these groups have non-trivial second bounded cohomology, right? The area of a triangle is at most pi. So it's not true that the second bound cohomology vanishes. Therefore, it can't be that there's a space in which it acts 3 times ergodically. That's interesting, isn't it? I mean, right? It just can't be. You can't find a measure space like that. Okay. And so now, if I want to move in the general direction of a proof of of a theorem, I should convince you that for some groups related to transformations of the Euclidean space, diffeomorphisms say, I can find a space that is amenable, and it is k ergodic for every k. Right? And that's what I want to convince you of now. And this requires one last concept, and it's what group theorists like to call lamplighter groups. So the idea of a lamplighter group is you have to imagine that you have a long street represented by the group Z, and that on every block of this street there's a traffic light represented by the group Z mod 2 or Z mod 3 if you believe in the color orange. And the lamplighter consists in traveling on this road and flipping the switches. So your group will consist in elements of Z and configuration spaces of traffic lights on the road. And so here's the formal definition. So given any group G that now represents the traffic lights, it can be you know, three states or any group. Okay, define the lamplighter W stands for Rees product. So W, the notation in group theory is that you take G and you do the Rees product, which is an integral sign, with Z, integral because of sum. And the algebraic definition is, well, you start by taking a copy of G for every site on your road. So this direct sum means the restricted product. So you take all sequences that have only finitely many non-trivial lamps. And you do the mapping torus or the semi-direct product with Z acting by shifting the coordinates along your streets. All right, that's the lamplighter group. So it's a group that contains G, but it's larger. All right, so the theorem is that whatever the group G is, in this circumstance, the lamplighter will always admit an amenable, infinitely ergodic space. So again, my group will be countable if I want to do standard ergodic series. So for any G, there exists an amenable, infinitely ergodic W space for this larger group. And all right, and before giving you the proof of this theorem, because that's why we're going to play with some elementary ergodic theory, I want to tell you why this theorem will imply the vanishing of the bound cohomology of at least the compactly supported transformation groups in any regularity. And for the non-compactly supported, it's considerably harder, and that's our follow-up article with Sam and Francesco. So I just want to say that here's a corollary, and for this I'm going to phrase it in some sort of general statement. Okay, so let H be a group acting on a set, so a group of transformations of a set Z. Okay, so H could be compactly supported diffeomorphisms, and Z could be RD, for instance. Right, but I want to abstractify it. So suppose there exists some subset Z0 in Z, and some element in the group H0 in H, with the following two conditions. Number one, all the H0 translates of Z0 are disjoint. So Z0 does not meet H0 to the P Z0. So this is empty for all positive powers. Okay, so H0 displaces this set. So you really have to think of this picture that you see here, right? It's really, you should think of the master trick here, the application trick. So that's, and number two, any finite set in the group, so any finite set, I don't know, F in H, can be conjugated to be supported in Z0. Okay. Again, this is a situation that you have clearly in all these compactly supported transformation groups. You know, if Z0 is some compact set you choose from the beginning, any finite family of compactly supported transformations can be conjugated into that guy. Right? So under these abstract circumstances, the group H will have no bound cohomology whatsoever. Then, so I have another H here. Then the bound cohomology of H vanishes in every degree. And I claim that this is a consequence of the previous theorem. And I have to make a choice. My choice will be to prove the ergodic theorem and not deduce the corollary. But the idea is that just by looking at the group support on Z0 and all its translates, you see a lamplighter group. And that's the key point. So now in the last minutes, I want to prove the ergodic theorem. So I want to prove that whenever you have such a lamplighter, which occurs, for instance, in the situation here where you do this duplication, then I can manufacture for you an interesting measure space which will be amenable and k-ergodic for any k, so infinitely ergodic. And the proof of this theorem is, in a sense, very naive. So the measure space will be a very explicit one, but will hopefully invite you to, like this type of measure theory, because there's magic happening here. So here's how I want to do it. So I didn't write the proof in my notes because I was assuming I would remember it. So proof of theorem. I'm simply going to write down a formula x equals something. Okay, so this risk product should act on some measure space x. All I have is an abstract group G and this construction. So I'm going to start by considering G itself as a measure space. That means I have to choose, we agreed that G can be countable, right? So I'm going to choose some probability distribution on G. So let mu be full support, that's why I use countability, full support probability measure on G. Okay. So now G mu is a measure space. It's a very stupid one, and we don't need to invoke measure theory for that because it's just atomic. I put a little weight on every point of G. But the reason I do that is because I can do something in the category of measure spaces that you cannot do easily in the category of groups. Namely, I can form an infinite product and remain in the very smooth category of probability spaces. So here's what I consider. I consider X to be, by definition, the infinite product indexed by Z of the naive measure space G mu. And now this is not naive anymore at all. This is a non-atomic space. Right? Unless G is the trivial group, it is non-atomic. Even if G is the group of order 2, this is a complicated measure space. And the claim I'm making is that even though it's an infinite unrestricted product, which is therefore much huger than this restricted product or sum, I claim that in fact it is much smaller. It is smaller because we take the product in the sense of measure spaces, meaning that we have a lot of null sets that we can neglect, and that's what will make everything work. So let's have a look. First of all, W acts indeed on X, because the restricted product, of G acts on this infinite product, and Z acts by shuffling the coordinates, right? There's something to note here. Since my group G is not finite, this measure cannot be invariant. I chose a distribution on G, but it cannot be invariant. Meaning when I act on this, I get Radon-Nicodim derivatives. I don't preserve the measure. And so this is all a bit trivial on the group itself, but I have an infinite product. So it is crucial here that in the lamplighter, I only have finite products. Otherwise, they actually become singular. It's not non-singular anymore, right? An infinite product of non-singular transformations can very well be singular. All right, so I have this action. And I claim that it's amenable and infinitely ergodic, and this I can do probably even waving my hands, because look, why should it be amenable? The action of this subgroup here is amenable because essentially it's a regular action, right? For any given group element here, you just shift on one or finitely many coordinates. So that was the trivial example of an amenable action. Now, this group is only a normal subgroup of my big group, but what is missing is Z, and we know already from Banach that you can average anything on the Z. The Z is amenable. So this action is amenable. And why is it now infinitely ergodic? It is infinitely ergodic because even just the action of Z on X is k-ergodic for every k. Okay, so why is it ergodic for k equals 1? And I'll be done after this. This is sometimes called the Kolmogorov 0-1 law. Right? If you have some measure space and you take an infinite product on the Z, and you shift this with Z. The fact that this is ergodic is Kolmogov's-Zeron law that tells you you can't have any, you can't define any measurable invariance that is a tail invariance, tail equivalence relation invariance. And now that's k equals 1. Now if I take higher k, I just have to observe that k copies of x, it's k copies of an infinite product of something, right? I write omega, but this was g. And this is the same as the infinite product of omega to the k. So again, Kolmogorov-Zeron law just applied to a larger state space. And so that's the proof, and I'll end here.